At 11:19 in the evening Eastern Time on the 29th of March 2026, something broke inside the Sun. Not metaphorically. Deep within the magnetic labyrinth of active region 4405, a violent reconnection event tore through the coronal architecture and unleashed an X 1.4 class flare, the most powerful solar outburst recorded in nearly 2 months. High-energy photons ripped across 93 million miles of vacuum at the speed of light and slammed into the day side of Earth before most people had even noticed the alerts. But here's the thing. Buried inside the telemetry from that eruption is an anomaly, a specific geometric paradox embedded in the kinematic profile of the ejected plasma cloud that our standard magnetohydrodynamic models simply cannot account for on their own. The initial ultraviolet signature pointed to a tightly localized coronal collapse, a sharp, contained implosion of magnetic tension. So why is the resulting coronal mass ejection expanding at 1,870 kilometers per second with an asymmetrical density gradient that is skewed hard toward one lateral edge? That discrepancy is not noise, it is a clue. And once you understand what it points to, the threat picture for the next 48 to 72 hours changes completely. Before we get there, though, let's walk through what actually built up to this eruption, because the sequence matters enormously. Russian and international solar observatories had been watching active region 4405 for weeks, specifically tracking a rapid, almost rhythmic accumulation of torsional stress within the magnetic flux topology of that region. The photosphere operates like a churning ocean of superheated plasma, driven by deep convective currents beneath it. Those currents drag internal magnetic field lines up to the surface, where they punch through as dark sunspot pairs. When the sun's differential rotation, faster at the equator, slower at the poles, begins braiding and twisting those flux tubes together, the system starts banking enormous amounts of potential energy. Think of it like winding a steel spring tighter and tighter, each rotation adding to the stored load until the metal itself starts groaning. On the 28th of March, that groaning became audible in the data. Active region 4405 began releasing a rapid volley of minor C-class flares, alongside one more energetic M1.3 event. By the 29th, acoustic oscillations probing the solar interior revealed deep structural shearing, accompanied by 4 additional C-class eruptions in the same region. These were not coincidental minor events. They were foreshocks, the localized snapping of smaller magnetic bands, each one fractionally releasing the stored tension, like individual steel cables popping on a suspension bridge right before the main span gives way. Then, on the 30th, the main event, the X 1.4 classification. To feel the weight of that number, remember that the X-class scale is logarithmic, and that a single X-class flare releases tens of thousands of times more total energy than the entire global electricity generation of humanity, all discharged in a matter of minutes. The field lines in active region 4405 reached their breaking point, snapped, and instantaneously reconnected in a lower energy configuration. The energy liberated by that transition flash-heated the surrounding coronal plasma to tens of millions of degrees and sent the global solar activity index spiking into critical territory. If you have been following this story and you want every update the moment the data changes, now is the moment to subscribe. because what is unfolding over the next few days is moving fast and the details matter. Back to the sequence. Something deeply unsettling in that rapid succession of flares deserves attention beyond just the immediate energy release. The data suggests the magnetic framework of the entire northern solar hemisphere is currently oscillating like a struck bell, with stress potentially propagating into neighboring sunspot groups rather than simply dissipating. Whether that represents a cascading destabilization or a controlled bleed-off of accumulated tension is still being actively debated. What is not being debated is the immediate consequence that arrived at Earth well before the main plasma cloud did. The moment the electromagnetic radiation, specifically the X-ray and extreme ultraviolet wavelengths, reached the sun-lit hemisphere, the D region of the ionosphere, sitting roughly 60 to 90 kilometers above the surface, absorbed it like a sponge. Under normal conditions, that region is relatively transparent, and high-frequency radio waves bounce cleanly off the denser upper layers, curving over the horizon and enabling transoceanic communications. The extreme ultraviolet pulse from the X 1.4 flare violently ionized the neutral nitrogen and oxygen atoms in the lower D region, stripping electrons free and generating a thick, plasma-dense layer that absorbs radio signals rather than reflecting them. It is the electromagnetic equivalent of dropping a lead-lined curtain over the sky. Commercial aviation on transoceanic routes, maritime communications coordinating global shipping, and hardened military radar systems were instantly degraded or entirely silenced, completely indifferent to how sophisticated the hardware on the receiving end happened to be. The practical stakes of that blackout stretch further than simple inconvenience. Consider that the margins in astrodynamics are measured in fractions of a second. A trajectory correction burn for a spacecraft accelerating out of Earth orbit requires precise telemetry uplink, confirmed receipt, and verified execution within tight timing windows. The Sun just demonstrated, cleanly and without warning, its ability to sever those communication tethers entirely. Radio blackouts are fleeting. They dissipate as the ionosphere recombines once the flare subsides. But the physical object the Sun launched into interplanetary space does not dissipate. It travels. The coronal mass ejection spawned by active region 4405 is currently crossing the inner heliosphere at 1,870 kilometers per second. Let that velocity settle for a moment. At that speed, the plasma cloud would cover the distance from New York to Los Angeles in roughly 2 seconds. It is moving through the ambient solar wind like a supersonic plow, driving an immense shock wave ahead of it that compresses the interplanetary magnetic field and generates a turbulent sheath of accelerated solar energetic particles. Protons and atomic nuclei stripped bare of their electrons and pushed to relativistic velocities. The region between that forward shock wave and the dense core of the cloud is one of the most energetically hostile environments in the inner solar system when a major eruption is in transit. Here is where the trajectory assessment gets complicated and where that density asymmetry becomes critically important. Coronagraph imagery from tracking networks placed the bulk of the ejection on a trajectory, showing an estimated 40-degree offset from Earth's current orbital position. In standard space weather analysis, a 40-degree divergence is generally treated as a near miss. The dense magnetic core of the flux rope, carrying the highest field strengths and the most concentrated plasma, threads past Earth's position without direct engagement. What remains is a glancing blow from the peripheral edge of the expanding cloud. Think of a massive heavy displacement speedboat tearing across a still lake at full throttle. You are positioned well clear of its direct path, but the violent wake it generates rolls outward and hits your small canoe anyway. Whether that wake capsizes you or just rocks you hard depends entirely on one variable that remains hidden until the very last moment: the magnetic orientation of the incoming plasma. Specifically, whether the embedded interplanetary magnetic field is pointing northward or southward when it reaches the Deep Space Climate Observatory at the L1 Lagrange point, roughly 1.5 million kilometers upstream from Earth. If that field points northward, it aligns with Earth's magnetosphere and the interaction stays relatively benign. If it points southward, it opposes our magnetic shield through a process called day-side magnetic reconnection, and the two fields link together, opening a direct channel that pours solar energy into the magnetosphere like water through a broken dam. The forecasters at NOAA's Space Weather Prediction Center will not know the answer to that question until the cloud hits the L1 satellite, giving them roughly 15 to 45 minutes of warning before Earth impact. That is the irreducible uncertainty sitting at the center of every risk calculation right now. Given the trajectory and preliminary cloud parameters, NOAA has formalized a G2 moderate geomagnetic storm watch targeting the 31st of March. The baseline KP index, the logarithmic scale from 0 to 9 measuring horizontal deviations in magnetometer readings, is currently hovering around 3 to 4, holding in a state of suspended anticipation. Early modeling suggested roughly a 17% probability of a full magnetosphere compressing storm with a 40% probability for minor disturbances. But here is the thing about those percentages. They are derived from static models built around standard single eruption plasma geometries. And, as we will get to shortly, the geometry of this particular ejection is anything but standard. What are you most concerned about heading into the March 31st window? The Artemis timeline, the power grid exposure, or the possibility of the storm escalating past G3? Drop it in the comments because the answer genuinely shapes which part of this analysis matters most to you. A G2 event produces geomagnetically induced currents in high-latitude electrical infrastructure. These are not theoretical currents flowing through abstract circuit diagrams. They are real, measurable flows of electricity induced in the ground and entering power transformers at vulnerable nodes in the grid, triggering voltage alarms, thermal overloads, and forced rerouting of regional power loads. The thermosphere simultaneously absorbs the storm energy and expands outward into space, increasing atmospheric drag on low Earth orbit satellites and forcing operators to execute emergency thruster burns to prevent gradual orbital decay. If the storm escalates to G3 conditions, which aggressive modeling threads consider plausible given the uncertainty in the magnetic orientation, the threat profile shifts significantly. Satellite navigation systems experience intermittent degradation. Low-frequency radio navigation suffers heavy interference, Surface charging on satellite components increases, raising the risk of electrostatic discharge capable of damaging avionics. These are not worst-case hypotheticals. These are documented consequences that have occurred during previous G3 events. The mathematical question is simply whether this particular interaction will cross that threshold. Now here is where the timing becomes almost unbearable in its tension. NASA is in final countdown operations for Artemis II. The targeted launch window opens on the evening of April 1st, with T0 designated for around 6:24 in the evening Eastern Time. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are currently in pre-launch quarantine, preparing to become the first human crew to travel beyond low Earth orbit since Apollo 17 departed the lunar surface in December of 1972. Their trajectory pushes the Orion capsule farther from Earth than any person has traveled in over half a century. Achieving translunar injection requires accelerating to roughly 25,000 miles per hour, a burn that carries them cleanly through the Van Allen radiation belts and out beyond the protective bubble of Earth's magnetosphere. That distinction is everything. The International Space Station and virtually every operational crewed spaceflight of the modern era have remained inside the magnetosphere, receiving substantial passive radiation protection from the planet's magnetic field. Artemis II deliberately exits that protection. The crew will be exposed to the full open ocean conditions of interplanetary space. If the coronal mass ejection cloud, traveling at 1,870 kilometers per second, arrives with sustained elevated particle flux during the ascent and early translunar phase, the astronauts could be flying through a dense stream of solar energetic particles with minimal shielding between them and the radiation source. Even before worrying about the biological exposure in deep space, the ascent phase itself presents a specific hardware vulnerability that does not get enough attention. A localized spike in highly charged particles during the climb through Earth's upper atmosphere can trigger what aerospace engineers call a single event upset in the flight computers. A single high-energy heavy ion striking a microchip and flipping one binary bit, 0 to 1 or 1 to 0, in the wrong register at the wrong moment. Modern guidance algorithms running in the Space Launch System's avionics during maximum dynamic pressure carry no tolerance for corrupted bytes. A single bit flip in the guidance code could trigger an automated abort sequence. In the worst-case scenario, it could cause a deviation from the flight path that the system cannot correct in time. Layer on top of that the possibility of geomagnetic storm conditions, degrading the telemetry relays between the vehicle and ground control, and you have a scenario where flight directors are partially deaf while 4 human beings sit atop millions of pounds of liquid hydrogen and liquid oxygen. The Artemis II launch team will be making a go or no-go decision with incomplete information in a rapidly evolving space weather environment, with margins they cannot fully calculate in advance. If the launch succeeds and Orion achieves translunar injection, the threat vector shifts entirely from hardware vulnerability to biological exposure. In deep space, solar energetic particles do not simply pass harmlessly through the spacecraft hull. When those high-velocity protons and stripped atomic nuclei strike the aluminum alloy structure of the crew module, they shatter atomic nuclei within the metal and generate a secondary cascade of high-energy neutrons and brimstolling radiation. That secondary shower penetrates deeply into the interior of the capsule. In biological tissue, the damage mechanism operates at the molecular level. The particles ionize water molecules inside cells, generating highly reactive free radicals that attack DNA and cause double-strand breaks in the genetic code. An acute, high-dose exposure overwhelms the human body's cellular repair mechanisms entirely, producing acute radiation sickness in the short term and dramatically elevated cancer risk long term. The Orion capsule incorporates a dedicated radiation storm shelter in the lower bay of the crew module, using the mass of onboard water reserves and dense structural components to attenuate particle flux. The problem is that accessing the shelter and staying there requires advance warning, and it requires the spacecraft to be in a flight phase, where crew mobility is not constrained by active maneuver sequences. The early translunar phase, when trajectory geometry is mathematically rigid, is precisely the window when options narrow. Back on the surface, the incoming solar material carries its own set of consequences for populations nowhere near a launch pad. The field of geomagnetobiology documents a well-researched intersection between geomagnetic disturbances and human physiology. When the coronal mass ejection compresses Earth's magnetosphere, it induces global fluctuations in the geomagnetic environment and drives ultra-low frequency electromagnetic waves, Schumann resonances, into ranges that interact with the human autonomic nervous system. The pineal gland is particularly sensitive to changes in ambient magnetic field strength. During elevated geomagnetic activity, rapid fluctuations can artificially suppress melatonin secretion, disrupting circadian rhythms and producing cascading sleep disruption across the affected population. Independently, electromagnetic interference can affect baroreceptors in the vascular system, causing unexpected constriction or dilation of blood vessels and manifesting as the blood pressure spikes and severe migraines that medical professionals consistently observe during elevated space weather events. For those who are weather sensitive, the guidance going into the March 31st window is specific. Prioritize 7 to 8 hours of uninterrupted sleep to counteract the anticipated melatonin suppression. Maintain aggressive hydration to support blood volume and vascular stability. Favor light, nutrient-dense meals rich in raw fruits and vegetables which provide antioxidants to buffer oxidative stress at the cellular level. Limit alcohol and caffeine strictly. Both are vasoconstrictors that will compound existing cardiovascular tension during the peak impact window. Avoid intense physical exertion during the hours of maximum storm activity. Anyone managing pre-existing heart conditions, hypertension, or cardiovascular disease should keep prescribed rescue medications immediately accessible and monitor vitals closely. If a G3 level event materializes and a statistically significant wave of physiological stress responses coincides with regional power grid degradation and voltage sags, the intersection of cosmic physics and fragile human biology creates a domestic health situation that is easy to underestimate until it is already happening. Looking past the immediate 31st of March window, the solar activity forecast for early to mid-April is not reassuring. Analysts have already flagged elevated geomagnetic disturbance potential during April 1st and 2nd, directly overlapping the Artemis II launch parameters, as well as the 6th, the 10th and 11th, and the 16th. A larger and more structurally complex alignment is approaching between the 18th and 21st, with early indications of a potential G1 level storm developing specifically around the 17th. This sustained barrage is not coincidental. It is the direct expression of solar cycle 25 approaching its maximum phase. The Sun is currently undergoing the magnetic pole reversal that defines the cycle peak, a process accompanied by a surge in sunspot frequency, expanded coronal hole activity, and the frequency of explosive events like the X1.4 eruption we are analyzing. The solar magnetic field is fractured and chaotic. The star is cycling through a period of structural instability and firing high-velocity plasma into the interplanetary medium with regularity. We are inside the active zone, and we will remain there. There is a significant upside buried in all of this for those positioned to see it. If the March 31st impact delivers even a moderate geomagnetic storm, sky watchers across the northern tier of the United States and into Canada could witness genuinely spectacular auroral displays. The mechanics of the aurora are a direct readout of the storm's intensity. Charged particles funneling down the magnetic field lines into the polar regions collide with oxygen and nitrogen molecules in the upper atmosphere, exciting those atoms and causing them to emit light as they return to their ground state. Oxygen atoms higher in the atmosphere produce rare, deep red hues. Lower oxygen produces the classic brilliant green ribbons. Nitrogen adds blue and violet tones. If the storm pushes into G3 territory, the auroral oval, the ring of luminous activity encircling the magnetic pole, expands dramatically southward, potentially bringing the display within sight of tens of millions of people who have never seen it. That light is not decorative. It is the visible exhaust of an energy dissipation system running at capacity, protecting the atmosphere from being gradually stripped away by the solar wind. The beauty of it is real. So is the violence producing it. Now, back to the anomaly, the geometric paradox at the heart of this event. Standard magnetohydrodynamic models are unambiguous on this point. A localized magnetic collapse should produce a relatively symmetrical, expanding plasma bubble, roughly analogous to an inflating balloon. What we are tracking instead is an ejection moving at 1,870 kilometers per second with a pronounced asymmetrical density concentration pushed hard toward the 40-degree lateral edge. The initial UV signature pointed to a contained, symmetric source. The output does not match the input. That discrepancy requires an explanation, and the answer is buried in the foreshock sequence from March 28th. Look at the M1.3 event from active region 4405 on the 28th. Retrospective analysis of the extreme ultraviolet data reveals that the M1.3 flare quietly launched a stealth coronal mass ejection. Slower, far less dense, and carrying no detectable ultraviolet or radio signature, significant enough to trigger automated alerts. This invisible cloud began drifting outward from the Sun approximately 24 hours before the main X1.4 eruption. When the X-class flare detonated on the 30th and launched its hypervelocity plasma cloud along essentially the same trajectory, the laws of kinetic physics made the outcome inevitable. The faster massively energetic ejection caught the slower stealth cloud from behind and drove directly into it. A high-speed rear-end collision in the interplanetary medium, occurring somewhere between the Sun and Earth, completely invisible to any observing instrument. The process of two plasma clouds merging through forced compression is called CME cannibalization, and it produces what astrophysicists classify as a merged interaction region. The two magnetic flux ropes, forced together under enormous compressive pressure, became a single, structurally deformed cloud. Because the initial stealth ejection had a slightly offset trajectory relative to the main event, the collision was not perfectly symmetric. The compressive force squeezed the combined plasma mass out toward one lateral edge, the 40-degree edge, creating precisely the asymmetrical density gradient the coronagraph imagery showed us. The paradox is resolved. The anomaly is not a modeling error. It is a collision signature, a fingerprint left by an invisible impact that happened in the dark between two worlds. Wait, it gets worse. Because the dense merged interaction region has been pushed into the peripheral edge of the expanding cloud, the exact edge categorized as delivering the glancing blow to Earth's magnetosphere. The anticipated impact on March 31st into April 1st is not simply carrying the energy of a secondary wave from a near miss. It is carrying the combined, compressed density of two separate solar eruptions, concentrated into the precise part of the structure that is going to intersect with Earth's magnetic field. The 17% full storm probability estimate and the 40% minor disturbance figure from NOAA's early models were built on the assumption of a standard single eruption plasma profile. Those models did not incorporate the existence of the stealth ejection or the merged interaction region, because that data became available only through retrospective analysis of the foreshock sequence. The actual kinetic momentum in the incoming lateral wave is likely substantially higher than those preliminary figures reflect. This is the situation as it stands. A cannibalized, asymmetrically compressed plasma cloud carrying the merged energy of two eruptions is inbound, with its densest region aimed at a glancing intersection with Earth's magnetosphere. The magnetic orientation will remain unknown until the Deep Space Climate Observatory measures it, at which point the window for meaningful response collapses to minutes. 4 astronauts are in quarantine preparing to launch into that same environment approximately 24 hours after peak storm impact. Forecasters at NOAA are running models built on incomplete geometry, issuing probabilistic predictions that NASA flight directors must use to make irreversible go or no-go decisions for the most significant human spaceflight mission in 5 decades. If this analysis has sharpened your understanding of what is actually converging over the next 72 hours, consider liking it. It directly helps this kind of rigorous space weather analysis reach more people at the exact moment it matters. The Sun has chosen an extraordinary moment to demonstrate the full range of its behavior. We have spent decades building the technological architecture of modern civilization on the assumption of a relatively stable heliospheric baseline. Active Region 4405 just reminded us how thin that assumption actually is. The coming hours demand flawless execution from every team interpreting the incoming telemetry, and quiet, extraordinary courage from 4 people sitting in quarantine, waiting for a launch window that the star 93 million miles away may yet decide to close.